What is up, my guys and girls? Today we are talking about the revival of learning in Western Europe. Today's topics will include the decline of learning in Europe, introduction of Arabic numerals, the revival of mathematical learning, and of course Fibonacci and his famous sequence. So, where do we even start? Well, let's start with what mathematicians used before. These things. Letters? Numbers? Who even knows? The important thing to note is that these were not invented to look fancy, even if that's what their primary purpose is today. This begs the question, why do Roman numerals suck in mathematics? Example time. Let's solve 14 minus 5. Easy. Almost an insult to your intelligence to even ask. Now let's try the same problem, utilizing Roman numerals. 14 becomes xiv, and 5 is just v, so taking away a v from the xiv should give us 11. Right?
Nope.
But now let's try 16 minus 5, which gives us xvi minus v. Now, we take away the v again, but this time we don't reverse the xi. Now try adding or subtracting even bigger numbers.
Nope, 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 nope.
What about algebra, or God forbid, calculus? So, where do we get 1, 2, and 3 from I, and I? Of course, we just go to the holy land of inventions, India. At the very top, we see the numbers 1 through 9 written in Brahmi, which eventually through some shenanigans involving crusades and jihads, gets us to the 1 through 9 we know today. This guy also helped. You may have heard of him. He's just a little famous. Wait, we're still missing one of the most important components. We're missing nothing. Why is 0, which is literally the manifestation of all things related to your interest in the secret history, so important? 0 acts as an important placeholder. Whereas in the Roman system, you just add an x, or use a bigger letter like L to count up by tens. We use a 0 to represent the addition of a 10 in the Arabic system. 0 is also the concept that enables us to define the integer. In the Roman system, anything below 1 is about as real as getting 100 on a math topics test. In the Arabic system, we face no difficulties moving across from positive to negative because we have the concept of 0 to define said boundary. So, how did this idea, which originated when some Indian mathematicians found that counting by tens is easier than counting by 12s, find its way into Europe? Well, remember this guy? Don't? There will be a graded 10-point quiz after this. If you fail, this will be a betrayal of my trust. So, from India, the Arabs also liked the idea, and brought it with them along with them spices to North Africa, where young Fibonacci's father happened to be a customs official in the town of Bougie. Fibonacci learned from these traders the ways of counting to 10 and decided that it was much better than continuously adding x's, because after all, forcing someone to convert 4,499 into Roman numerals is probably the single worst thing you can do to them. So, what's the single most important thing we have in this world? Happiness? Wrong. It's money. Also, grades, but we choose to ignore those. So, Fibonacci found that buying spices was much easier using these Arabic numerals, which I should really call Hindu-Arabic numerals, because there was a massive argument a few years ago about the lack of recognition of the true origins of the numbers 1 through 9. So, what did the intrepid young Fibonacci do? Of course, he went and wrote a book. Books to be precise, though his first is more widely recognized. Why do we still remember these books from the 13th century, even though our history teachers will have us believe that the Tang dynasty is more important than basis of all modern mathematics? So, let's talk about probably Fibonacci's most famous work, the Liber Abbaci, the Book of Calculus. Notice the I at the end signifying the genitive case. Or was it ablative? Who even knows? Fibonacci divided his work into 4 parts, the most famous of which is section 3, which discusses the Fibonacci sequence, which you will all be sick of by the end of this video. Also important is section 4, which discusses the use of approximations and irrational expressions like square roots and irrational constants like pi. The Fibonacci sequence is created by utilizing the formula an is equal to an minus 1 plus an minus 2, where a1 and a2 are both equal to 1. Fibonacci initially utilized the sequence to calculate the population of rabbits in month n, taking the rules that we start with a single pair of rabbits, the rabbits take a month to grow up, and each rabbit taking 1 month to be born. Thus, the number of pairs of rabbits after month n is equal to the value an of the Fibonacci sequence. The single most famous mathematical constant associated with the Fibonacci sequence is the golden ratio. The golden ratio, defined as the ratio of A to B, where the ratio between A and B is equal to the ratio between the sum of A and B to A. It is known to have several properties, being able to explain the shape of an Nautilus shell, the dimensions of the Mona Lisa, and numerous other phenomena. The value of the golden ratio is intimately related to the Fibonacci sequence, with the ratio being equal to the limit as n approaches infinity of the ratio between two successive terms of the Fibonacci sequence. Imagine expressing pi using Roman numerals. The important parts of the Liber Abaci delve into the art of algebra. The first important part, inspired by an Egyptian mathematician, whose name I have experienced great difficulty trying to learn, delves into the systematic use of irrational numbers as solutions and coefficients in algebraic expressions. The second part discusses the use of geometry as solutions to algebraic problems. Now what about the Liber Quadratorum? The Book of Squares, despite being named as such, does not deal too much with geometry. Its name is a reference to the congruum problem, which Fibonacci proceeds to solve and prove over the course of the book, which involves exponents rather than shapes. Two parts of the book are of special interest to us: Fibonacci's solution to said congruum problem, and the Fibonacci identity. Given three integers, x, y, and z, find values such that the squares of x, y, and z are equidistant from each other. In other words, find values that satisfy the equation y squared minus x squared equals z squared minus y squared. Fibonacci proposed a parametric solution. Given two variables m and n, the value of the shown equation will always equal a congruum. In addition, multiplying any congruum by a perfect square will always yield another congruum. Fibonacci's identity, today called the Fibonacci-Brahmagupta identity, expresses the product of two sums of two squares as the sum of two squares in two unique ways. Fibonacci's identity allows us to multiply the squares of the absolute values of two complex numbers. It's time for a quiz. You must pass this quiz, or you have to subscribe. Question number 1. In which city was Fibonacci born, and in which country is said city located in? Question number 2. Which system was the primary numerical system utilized in Europe prior to Fibonacci? Question number 3. Why did Fibonacci first favor the Hindu-Arabic numeric system? Question number 4. From whom did Fibonacci gain inspiration for the Fibonacci identity? Question number 5. Which mathematician inspired Fibonacci to introduce the acceptance of irrationals as solutions to algebra? Question number 6. Which of Fibonacci's books delves in algebra? Question number 7. Where did Fibonacci first utilize his famous sequence? Question number 8. Find the value of a congruum given the values m equals 5 and n equals 3. No calculators, cheaters. Question number 9. Find the 15th term of the Fibonacci sequence. Question number 10. Calculate the value of parentheses, 12 squared plus 24 squared, closed parentheses, plus, parenthesis, 17 squared plus 23 squared, closed parenthesis, utilizing the Fibonacci identity. Thanks for watching, and remember, next time you see that building, remember the golden ratio and Fibonacci.